Well, in this video, we're going to talk about the memoryless property of exponential distribution. And what does that mean? What it means is that it doesn't matter that when the last arrival happened. The probability of next arrival being in 6 minutes or whatever, it doesn't change based on what happened in the past. Let's take one example. It says, so it essentially comes down to the event in each subinterval is independent of other subintervals as far as those subintervals are not overlapping. Probability of one arrival between 6:06 and 6:07 in the morning is independent of whether or not there was an arrival between 6:05 and 6:06 the minute before. The probability of the minute after is independent of the probability of the minute before. It is also independent of whether or not there was an arrival between 6:04 and 6:05, etc. In fact, probability of one arrival between 6:06 and 6:07 is the same, regardless of how long it has been since the last arrival. So, what are we headed with this? It means if you are waiting for an event to occur, then as you wait, you probabilistically are not getting closer to seeing that event, right? That's the memoryless property of exponential. If a random variable is following exponential distribution, it is memoryless. It does not remember what happened in the past. As you're waiting for that to occur, the probability of that occurring does not go up and down or down. Sometimes they say earthquakes follows that kind of distributions. Basically, probability of seeing the next earthquake does not go up because you have been waiting or no earthquake has happened in the past 100 years or something. Probability of that is still the same. So let's take a look at one example. It says, well, again, it's the continuation of the same example where customers are coming to a bank with a rate of 8.6 customers per hour. So that is the arrival process. And here it says, given that it has been 6 minutes, so it's a given. It has been 6 minutes since the last customer arrived. What is the probability that it takes at least 9 minutes until the next customer arrives, beginning from now? So that's the important part. So you're at the current time. The last customer arrived 6 minutes ago. And we're talking about probability that it takes at least 9 minutes to see the next customer from now. So it's always helpful to draw that little diagram. So it looks like customer n-1 arrived here, and then it has been 6 minutes, and this is now. It has been 6 minutes, and now you want to know, to see the next customer, which is customer n, what is the probability of this, which is a time between arrivals, essentially, from now to n as a t, at least 9 minutes. So basically t being greater than equal to 9 minutes. So the memoryless property essentially says it doesn't matter that it has been 6 minutes or 7 minutes or 10 minutes or 2 years. Probability of t greater than 9 minutes still will be calculated the same way. So to put that in mathematical format, probability of t greater than 9 minutes, given that, let's say, customer n-1 arrived 6 minutes ago, is just probability of t greater than 9. And to calculate that, you would have to change this to probability of t less than 9 so you can use the Cdf formula of exponential. So 1 minus probability of t less than 9. And that's the Cdf of exponential, where you would have 1 minus e to negative lambda x. Well, here we're talking in minutes, 9 minutes, but our lambda is in hours. So what we're going to do here to change the lambda to per minute. So 8.6 per hour divided by 60 minutes is going to give you 1.433 customers per minute. So make sure you do this conversion correctly and do not multiply to 60. That's a pretty common mistake. If you're seeing 8.6 customers per hour, you're going to see a fraction of that in a minute. So you divide that by 60. So that's our new lambda. It's in minutes. So e to the negative lambda x. Negative lambda x, so 0.1433 times 9. That is e to negative 1.29. So that's the probability of t or time between to see the next customer greater than 9 minutes. Or when it says at least, that's what it means, more than 9 minutes. Part B, given that it has been 12 minutes since the last customer arrived, what is the expected value of the time until the next customer arrives? Expected value. So we're calculating expected value given some past history. Again, that past history doesn't matter because it does not overlap with what we're talking about. We're talking about expected value of the next customer arrives, and the key piece of information is beginning from now. So that does not overlap with the past. As long as it does not overlap, we don't need to care about the past. So we're calculating expected value of seeing the next customer, essentially expected value of t given customer n minus 1 arrived 12 minutes ago. That is just expected value of t. Doesn't matter because it does not overlap. It's equal to 1 over lambda, so 1 over 0.1433, and that is 6.98 minutes. So on average, you're going to see the next customer in almost 7 minutes. And that doesn't change, Every time, the average time that you're expecting to see the next customer is about 7 minutes. So that was the memoryless property of exponential distribution.